Hello, YouTube fam. Get ready for an amazing video experience. Hello, YouTube friends. Join us as we unravel the mysteries surrounding primary line constants. The primary line constants are parameters that describe the characteristics of conductive transmission lines, such as pairs of copper wires, in terms of the physical electrical properties of the line. The primary line constants are only relevant to transmission lines and are to be contrasted with the secondary line constants, which can be derived from them, and are more generally applicable. The secondary line constants can be used, for instance, to compare the characteristics of a waveguide to a copper line, whereas the primary constants have no meaning for a waveguide. The constants are conductor resistance and inductance, and insulator capacitance and conductance, which are by convention given the symbols R, L, C, and G respectively. The constants are enumerated in terms of per unit length. The circuit representation of these elements requires a distributed element model, and consequently calculus must be used to analyze the circuit. The analysis yields a system of two first-order, simultaneous linear partial differential equations which may be combined to derive the secondary constants of characteristic impedance and propagation constant. A number of special cases have particularly simple solutions and important practical applications. Low-loss cable requires only L and Celsius to be included in the analysis, useful for short lengths of cable. Low-frequency applications, such as twisted pair telephone lines, are dominated by R and Celsius only. High-frequency applications, such as RF coaxial cable, are dominated by L and Celsius. Lines loaded to prevent distortion need all four elements in the analysis, but have a simple, elegant solution. In the upcoming section, we'll be dissecting the constants and exploring its implications in greater detail. There are four primary line constants, but in some circumstances some of them are small enough to be ignored and the analysis can be simplified. These four, and their symbols and units, are as follows. Name symbol unit. Unit symbol loop resistance R ohms per meter, loop inductance L henries per meter, insulator capacitance Celsius farads per meter, insulator conductance G Siemens per meters. R and L are elements in series with the line because they are properties of the conductor, and Celsius and G are elements shunting the line because they are properties of the dielectric material between the conductors. G represents leakage current through the dielectric and in most cables is very small. The word loop is used to emphasize that the resistance and inductance of both conductors must be taken into account. For instance, if a line consists of two identical wires that have a resistance of 25 ohm each, the loop resistance is double that, 50 ohm. Because the values of the constants are quite small, it is common for manufacturers to quote them per kilometer rather than per meter. In the English-speaking world, per mile can also be used. The word constant can be misleading. It means that they are material constants, but they may vary with frequency. In particular, R is heavily influenced by the skin effect. Furthermore, while G has virtually no effect at audio frequency, it can cause noticeable losses at high frequency with many of the dielectric materials used in cables due to a high loss tangent. Avoiding the losses caused by G is the reason many cables designed for use at UHF are air insulated or foam insulated, which makes them virtually air insulated. The actual meaning of constant in this context is that the parameter is constant with distance. That is, the line is assumed to be homogeneous lengthwise. This condition is true for the vast majority of transmission lines in use today. As we move forward, let's uncover the untold stories and fascinating intricacies of typical values for some common cables. Manufacturers commonly omit a value for inductance in their data sheets. Some of these values are estimated from the figures for capacitance and characteristic impedance by script-style ZLIC. Let's transition to circuit representation and uncover its significance. The line constants cannot be simply represented as lumped elements in a circuit. They must be described as distributed elements. For instance, pieces of the capacitance are in between pieces of the resistance. However many pieces there are and Celsius are broken into, it can always be argued they should be broken apart further to properly represent the circuit, and after each division the number of meshes in the circuit is increased. This is shown diagrammatically in Figure 1. To give a true representation of the circuit, the elements must be made infinitesimally small so that each element is distributed along the line. The infinitesimal elements in an infinitesimal distance script-styled are given by del lim x lx, drive lim x rx, bit lim x hx, lim x odx. It is convenient for the purposes of analysis to roll up these elements into general series impedance, Z, and shunt admittance, Y elements such that dz and dgx. Analysis of this network Figure 2 will yield the secondary line constants, the propagation constant, a script style gamma, whose real and imaginary parts are the attenuation constant, a script style alpha, and phase change constant, a script style beta, respectively, and the characteristic impedance, a script style Z, which also, in general, will have real, a script style R, and imaginary, a script style X, parts, making a total of 4 secondary constants to be derived from the 4 primary constants. The term constant is even more misleading for the secondary constants as they usually vary quite strongly with frequency, even in an ideal situation where the primary constants do not. This is because the reactances in the circuit A script style omega L and A script style I omega C introduce a dependence on A script style omega. It is possible to choose specific values of the primary constants that result in A script style alpha and A script style Z being independent of the Heaviside condition, but even in this case, there is still A script style beta which is directly proportional to A script style omega. As with the primary constants, the meaning of constant is that the secondary constants do not vary with distance along the line, not that they are independent of frequency. Let's now shift our focus to characteristic impedance and explore the ways in which it shapes our perspective. The characteristic impedance of a transmission line, a script style Z, is defined as the impedance looking into an infinitely long line. Such a line will never return a reflection since the incident wave will never reach the end to be reflected. When considering a finite length of the line, the remainder of the line can be replaced by A script style Z as its equivalent circuit. This is so because the remainder of the line is still infinitely long and therefore equivalent to the original line. If the finite segment is very short, then in the equivalent circuit it will be modeled by an L network consisting of one element of A script style Z and one of A script style D. The remainder is given by A script style Z. This results in the network shown in Figure 3, which can be analyzed for A script style Z using the usual network analysis theorems. Z0 delta Z alpha Z's A delta Y, which rearranges to ZZ A delta Z alpha delta Z delta Y, taking limits of both sides. Lim delta x to Z A delta Z equals Z alpha Z, and since the line was assumed to be homogeneous lengthwise, Z alpha Z. Let's now shift gears and explore propagation constant through a critical lens, uncovering its strengths and weaknesses. The ratio of the line input voltage to the voltage at distance A script style delta X further down the line, that is, after one section of the equivalent circuit, is given by a standard voltage divider calculation. The remainder of the line to the right, as in the characteristic impedance calculation, is replaced with A script style Z. A frac via math move X A frac deltas fracs 0 delta I's A delta I fracs 0 delta I's A delta Y equal 1 A frac deltas delta Y. Each infinitesimal section will multiply the voltage drop by the same factor. After A script style N sections, the voltage ratio will be A frac via math move X left 1 A frac deltas delta I right. At a distance A script style X along the line, the number of sections is A script style Xi delta X, so that A frac via math of X left 1 A frac deltas delta I right frac Sir delta X. In the limit as A script style delta Xito. A frac via morphm of x lim delta xito a frac via morphm of x lim delta xito a left one a frac deltas delta I right frac sir delta x. The second order term a script style deltas delta y will disappear in the limit, so we can write without loss of accuracy. A frac via morphm of x lim delta xito a left one a frac deltas a right frac sir delta x. And comparing with the mathematical identity, I equal lim tone fin upux, yields via morphm I equal vx e frax x. From the definition of propagation constant, vi vx. Hence, gamma frax cert z. As we embark on the next leg of our journey, let's unpack the layers of ideal transmission line and examine its core elements. An ideal transmission line will have no loss, which implies that the resistive elements are zero. It also results in a purely real resistive characteristic impedance. The ideal line cannot be realized in practice, but it is a useful approximation in many circumstances. This is especially true, for instance, when short pieces of line are being used as circuit components such as stubs. A short line has very little loss, and this can then be ignored and treated as an ideal line. The secondary constants in these circumstances are gamma equal e omega squatalk 0, beta omega squatalk z0 cert fractalk. With the groundwork laid, let's now examine twisted pair and its connections to our previous discussions. Typically, twisted pair cable used for audio frequencies or low data rates has line constants dominated by R and Celsius. The dielectric loss is usually negligible at these frequencies and G is close to zero. It is also the case that, at a low enough frequency, a script style ridge omega L, which means that L can also be ignored. In those circumstances, the secondary constants become a gamma prux assert I omega cr, alpha prux assert frac omega cr, a beta prux assert frac omega cr, z a prux assert frac omega c cert frac omega c I cert frac omega c. The attenuation of this cable type increases with frequency, causing distortion of waveforms. Not so obviously, the variation of a script style beta with frequency also causes a distortion of a type called dispersion. To avoid dispersion, the requirement is that a script style beta is directly proportional to a script style omega. However, it is actually proportional to a script style skew omega, and dispersion results. A script style z also varies with frequency and is also partly reactive. Both these features will be the cause of reflections from a resistive line termination. This is another undesirable effect. The nominal impedance quoted for this type of cable is, in this case, very nominal, being valid at only one spot frequency, usually quoted at 800s or once. In the next segment, we'll be exploring coaxial cable and its implications for our subject matter. Cable operated at a high enough frequency, medium wave radio frequency or high data rates will meet the conditions a script style Br omega L and a script style G omega C. This must eventually be the case as the frequency is increased for any cable. Under those conditions, R and G can both be ignored except for the purpose of calculating the cable loss, and the secondary constants become a gamma prox e omega squatalk, alpha prox a frac dirk circelk a frac lefts 0g a fracas a right a prox a fracras, a beta prox omega squatalk, z a prox a cert fractalk. Prepare yourself for an in-depth analysis of loaded line in this section. Loaded lines are lines designed with deliberately increased inductance. This is done by adding iron or some other magnetic metal to the cable or adding coils. The purpose is to ensure that the line meets the Hebesid condition, which eliminates distortion caused by frequency-dependent attenuation and dispersion, and ensures that a script style Z is constant and resistive. The secondary constants are here related to the primary constants by gamma cert erg plus e omega squatalk, alpha cert erg, beta omega squatalk, z0 cert fractalk cert fracreg. Let's now turn our gaze towards velocity and explore the fascinating connections it has to offer. The velocity of propagation is given by Vf since f and beta frac a pi lambda, then v frac omega beta, in cases where can be taken as beta omega scuttleq. The velocity of propagation is given by v equal I over cirtulq. The lower the capacitance, the higher the velocity. Within a dielectric cable, which is approximated to with low loss cable, the velocity of propagation is very close to c, the speed of light in vacuum. If you found this video helpful, give it a like and share it with someone who might benefit from it.